Houman Owhadi is professor at CALTECH Institute, and we're going to talk about learning differential variables and learning.
Well, thanks for the introduction and thanks for the kind invitation. It feels like a very intimate place, so please feel free to interrupt me or take me on a tangent or different directions. And I mean, we can make this talk, I guess, interactive a bit. So I'm going to talk about two things. The first part of this talk, I think some of you have already heard it to some degree, so I apologize if this is the case. And the second part, I don't think that any of you have heard it, so that would be really new. The second part is something that we have been doing with DARPA. It's something that got me excited and concerned, and I will tell you why later. Okay. Okay, so to put this talk in context, observe that most problems within and beyond the scientific domain can be framed into one of the following 5 levels of complexity of function approximation. If you have already heard me give a talk, I started with 3, but now we're at 5, and we are trying to go beyond that. Okay, so type 1, approximate an unknown function given input-output data. So this is your classical interpolation problem. Type 2, assume that you have a collection of variables and edges indexed by the nodes and a collection of variables and functions indexed by the nodes and edges of a graph. Some of these variables may not be observed, and some of these functions may be unknown. I'm coloring them in red. The idea is that these variables are satisfying the functional dependencies imposed by the structure of the graph. Then, given n samples from subsets of the variables of the graph, approximate all the unobserved variables and unknown functions. Type 3, expanding upon type 2, if the graph structure itself is unknown, then use samples from the variables of the graph to discover its structure and approximate its unknown functions. Type 4, expanding upon type 3. Some variables may be unknown, and dependencies may become between variables may become stochastic as a result. And the problem is to use samples from the known variables to identify the graph of stochastic dependencies between these variables. So the type of problems that you see here are of the type digital twin modeling. I will not be talking about this here. And finally, type 5, given a problem, generate a graph to solve it with little or no data. Now, although Gaussian process methods are oftentimes seen as a well-founded but old technology limited to type 1 curve fitting, they can be generalized to solving type 2, 3, and 4 problems, all while maintaining the simple and transparent guarantees of kernel methods. But for these type 5 problems, you need something new, okay? And what I would like to do in this talk is to describe a Gaussian process solution to a type 2 problem, which is learning a PDE, describe a solution to a type 5 problem, which is learning an algorithm. And I would also like to discuss a little bit where this complexity ladder is taking us, okay? And this is what got me both excited and worried. I'll tell you why. Okay, so examples of type 2 problems include solving a nonlinear PD, learning an SDE, training a neural network, generative modeling, system identification, learning a PD, and I'm going to unpack this one here. And all these problems have the same Gaussian process-based solution, which is to replace all the unknown functions in these computational graphs by Gaussian processes, possibly independent Gaussian processes, and then compute their map or MLE estimator given available data and the structure of the graph. And this solution inherits the theoretical guarantees of kernel methods. And again, I will try to make this point in the setting of learning a PDE and its solution operator. So what I'm now going to present is just the unpacking of that problem. This part is a joint work with Yasemin Jalalian, Juan Felipe Osorio Ramirez, Alexandra Su, and Babdat Hosseini. I also refer to a forthcoming paper with Boumediene that started 3 years ago, but hopefully we'll get finished soon. Okay, so what I'm going to describe works for arbitrary nonlinear PDEs, but for ease of presentation, I'm going to describe the problem and its solution for a particular simple PDE, and then I'm going to generalize. So in this example problem, we want to learn the following nonlinear PDE, in which the functional form P of the PDE, that is mapping X, U, and its partial derivatives, is assumed to be unknown. The data comes in the form of partial observation of M unknown source solution pairs, which I'm going to write UIFIs. So for instance, we may be observing these solution terms at those red points and these source terms at those blue points. In practice, you can replace the pointwise observations of your solutions by tomographic measurements. So integrals along lines. Anything that is linear in the UIs is going to work for the framework that I'm going to describe. And our goal is to recover the unknown functional form P of the PDE, the partially observed solutions, and also the solution operator of the PDE, which is something that I will describe later on. Okay, so yes. You do not need to have red points on the boundary to recover P, but you need red points on the boundary if you're trying to learn the boundary operator and you're trying to learn the solution operator. So for the solution operator, yes, you need to know or learn the boundary operator. But for learning P itself, you don't really need points on the boundary because you can extrapolate to the boundary the P that you learn on the inside.
Xj, it is observed point, and X prime J, it is synthetic point. What is the difference between Xj and X prime J?
They're just points within the domain in which you have defined your PDE. They're arbitrary points at this stage.
Okay.
Eventually, I'm going to call these XJs observation points, and those I'm going to call them collocation points. They could be the same points. They could not be the same points. In practice, you are going to have more of those observation red points than the blue points, which we are going to call collocation points. Okay, so one popular method for solving this type of problems is SIND and its variant PDE find. And the idea behind this method is to interpolate partially observed solutions, take derivatives of the interpolants to create input-output data for this unknown functional form P, and then learn this P via sparse regression in a given library of functions. Right? So this has been a very popular method. Another popular method out there is sparse pins, and the idea is to replace all the unknown functions by neural networks, enforce the data and the physics into some loss for your neural network, and then recover a sparse representation of the functional form of the PDE in a library of symbolic functions via sparsity regularization. Okay, so if you're into deep learning, this is the kind of framework that you will use. The first one was more like compress sensing. Now, other learning methods for learning and possibly solving PDEs includes methods based on neural networks, and pins is a prototypical example of these methods. And here we're going to focus on Gaussian processes because while neural network-based methods are typically easier to implement and they benefit from extensive hardware and software support, these Gaussian process methods have more solid foundations, and they have a long history of interplays with numerical approximation. Now, this interplay with numerical approximation, earlier we were discussing with David, and we were saying that this interplay, in fact, is something that gets forgotten every 20 years and gets discovered in every 20 years. So you see Poincaré discovering this, then you see Sartre discovering it, it gets forgotten. Larkin rediscovers it again, gets forgotten. Then you see two communities discovering the same thing independently, information-based complexity, Bayesian numerical analysis gets forgotten, and then probabilistic numerics comes again. Okay, so, but it's a very old thing. Now, what I would like to do here is to introduce or present a kernel/GP method for PD/operator learning with a few desirable properties. So it's going to be interpretable, simple, and transparent. So if you are into kernel methods, this is why you like these kernel methods, because they have these properties. It is going to work with scarce data. Why? Because it's essentially an optimal recovery method. So we will have some notion of optimal, of minimax optimality with respect to the data. It will be robust to hyperparameter tuning. So I will unpack what I mean here. This is something important if you use the neural network method. You will see that these methods are not robust to hyperparameter tuning. And it will come with convergence and error bounds guarantees, and it will outperform existing methods. And again, I will unpack what I mean by all these bullet points. Okay, so going back to our example problem, where we want to learn the following nonlinear PD, in which we assume the functional form P of the PD to be unknown. Here I'm going to assume the data to come in the form of m pairs of source solution functions observed at the same n number of collocation points, right? Again, I'm doing this for ease of presentation. I'm coloring all these points in red here. And our goal at this stage is to recover the unknown functional form P of the PD and the partially observed solutions UI. Now, observe that learning this PD is equivalent to completing the following computational graph, in which nodes represent variables and edges represent functions. And here I'm coloring in red the unknown functions to be learned. So this corresponds to the unknown functional form of the PDE and the partially observed solutions. And our proposed approach is to simply replace the unknown functions by Gaussian processes. We're going to assume them to be independent, and then compute their map estimator given data. Now, if you write K for the kernel that you're going to use for your partially observed solutions, right? So this is a kernel defined on the input space of U. And if you write gamma for the kernel that you're going to use to recover P, so this is a kernel whose input space is the input space of P, then this method is equivalent to approximating the unknown functional form P and the partially observed solutions with minimizers of the following nonlinear optimal recovery problem, in which the loss is the sum of the squares of the RKHS norm of the unknown functions, and the constraints are enforcing the PD at the points at which we are observing the source terms, and they're also enforcing the values of the partially observed solutions at those observation points. Okay. Then we have the following theorem. If the field distance between those collocation points goes to 0 in this physical domain of the PD as their number n goes to infinity, so this is the mesh norm between your collocation points. And if the field distance between the partially observed input data points of P goes to 0 in a subset of the input space of P as m the number of source solution pairs and n the number of collocation points go to infinity. So here the idea is that we are not fully observing the input data points of P, we're only observing the x's. The values of u are those x's, but we are not observing the higher order partial derivatives, right? We're only partially observing these input data points. And here we are assuming that these partially observed input data points of P, they also fill a subspace of the input space of P. And then if P belongs to the RKHS space defined by the kernel gamma, and that kernel gamma has enough regularity so that its RKHS is continuously embedded in some subalert space HS prime for some S prime greater than the dimension of the input space of P over 2. So this makes sure that the elements of that RKHS are continuous functions. and if those partially observed solutions belong to the RKHS space defined by the kernel K, and that kernel K has enough regularity to be continuously embedded in some subspace HS for some S greater than the dimension of the input space, the dimension of the domain of the PD over 2 plus 2. So this makes sure that the PD is defined in a classical sense for the elements of that RKHS. And here we're also going to assume that those partially observed solutions are slightly more regular than belonging to the RKHS. I assume them to belong to HK squared, but any more slight additional regularity is enough for what I'm going to describe. Then the method converge. So as m goes to infinity and n goes to infinity, our approximate of p converges, where the convergence holds pointwise and in this Sobolev space, in this subset of the input space of p, and our partially observed solution, their approximate also converge, where the convergence holds pointwise and in this Sobolev space, and we have a priori error estimates. Okay. Now, what I would like to do is to give you some idea of the proof, because it's actually quite generic. Claim all type 2 problems can be proven to converge, and you can have error estimates for all these type 2 problems by just following this type of arguments. So the proof is articulated as follows. By the way, that's the only proof that I will put here. So bear with me. So because these UIs and FIs are solution pairs of our original PDE1, though this P and the UIs satisfy the optimization constraints of our nonlinear optimal recovery problem 2. Now, because Q and those VIs are minimizers of our nonlinear optimal recovery problem 2, the following inequality holds true uniformly in M and N, right? And once you have a uniform inequality like this, your problem becomes compact in a weaker space. And once it becomes compact, if your system is identifiable, your approximate are going to converge. So you see that this argument is quite generic. Now, the remaining part of the proof is classical stuff, and I'm just going to remind you what that classical stuff is, but it's very classical. So if you look at this inequality, you realize that those approximate of the partially observed solutions are going to have an RKHS norm that is uniformly bounded in N, the number of collocation points, because the RKHS space defined by the kernel K is continuously embedded in HS, and because those VIs are equal to those UIs at the collocation points, and because the field distance between collocation points goes to 0, our approximate of the partially observed solution is going to converge as the number of collocation points goes to infinity, and the convergence holds pointwise and in HG. So that's your classical kernel convergence result. Now, because the UIs are slightly more regular than just belonging to the RKHS space induced by the kernel K, we also have convergence in RKHS norm, right? So this is why I needed this additional regularity. And because we have our convergence in RKHS norm, I get that as n goes to infinity, the RKHS norm of our approximate of P remains uniformly bounded in M, the number of source solution pairs, by the RKHS norm of P, okay? And then the rest is again classical, right? So the RKHS space defined by the kernel gamma is continuously embedded in HS prime for some S prime greater than the input space of P over 2. The field distance between the partially observed input data points of P goes to 0 in a subset of the input space of P as M and N go to infinity. Those Qs and Ps are equal to each other at collocation points, and the VIs goes to the UIs as N goes to infinity, and then you get convergence, right? So the rest is kind of classical. It's technical if you have seen this kind of proofs before, but there is nothing special about it. A priori, yes, because well, typically you assume it to be compact. You need the field distance. Well, you need the field distance between your partially observed input points to go to 0. So you could not have it compact. It would give you a very slow rate of convergence. In practice, you take it to be compact, but yes, you could. The proof doesn't assume it to be compact, to be technical. Okay, so now let's generalize. So now we're going to consider the general problem. For the general problem, we want to learn the, we want to learn the following PDE and its solution operator. Now I'm going to write y for the input variable of corresponding to the domain of the PDE, because that variable may correspond to space or space-time. And again, we are going to assume the functional form of the PDE to be unknown. The data is going to come in the form of partial observation of source-solution pairs. And we're going to be interested in two problems. One is known as equation learning or discovery, which is to approximate the functional form of the PDE. The other one, which is becoming hot nowadays, is known as operator learning, and the problem is to approximate the solution operator associated with P, which is this map that is mapping the right-hand side to the solution. And here I'm going to assume the boundary condition to be known for ease of presentation, but if it's not known, nice, you will have to learn it to be able to invert the operator. But learning it is the same as what I'm describing here. Okay, so here we are going to place ourselves in a setting where learning the PDE is equivalent to learning the functional form of the PDE. What I mean by this is that we're going to assume that the action of the PDE on U evaluated at Y can be written as the composition of an unknown function, P, composed with this map phi, that is essentially a vector whose entries are Y and Q non-linear differential operators applied to U and evaluated at Y. So for example, if U PDE is the following non-linear parabolic PDE, then observe that this PDE can be written as this function P, so it's a classical function, of T and X, which becomes your variable Y, and of U and its partial derivatives, and those guys become your non-linear differential operators applied to U. Okay. Now, the data comes in the form of partial observations of M unknown source solution pairs. I'm going to write Ym for the points at which we observe those UMs. You don't. So very good question. So in practice, what you do is this. In practice, you make sure that you have enough of those guys, right? So you can have more is good, less is no good. Now, how do you know in practice that you don't have enough? When you try to solve the optimal recovery problem, the RKHS norm will go to infinity. So as you get more and more data, you P that is trying to replicate what you are seeing with some PDE will become more and more irregular. And when you have this is an indication of two things. Either you don't have enough derivatives, or the kernel that you have chosen for P is too smooth for the actual P that you are trying to approximate. So you will see through the misspecification as you get more and more data. And in fact, you can iterate this process, meaning that you can take a PDE that has too many of those derivatives. And because these Gaussian processes have a variance decomposition property, you can, after recovering P, you can go back and see how much each one of these derivatives explain the data that you have seen. And if you see that some of them don't explain the data much, you can truncate those terms from your kernel, and then you can do it again. So it's essentially a form of nonlinear ANOVA that you can do with these kernel methods. Okay. So I'm also going to write Y for the points at which we observe those Fs. We color them in white. And for simplicity, we are going to assume that all the observation points are contained in the collocation points. Again, this is for ease of presentation. And in practice, you are going to have more white points than red points. So more points at which you observe your Fs than points at which you observe your Us. And our goal is to learn those partially observed solutions, the functional form P of the PDE, from this data. Now, I'm going to describe two methods for solving this PDE learning problem. The first method, we're going to call it a two-step method because it can be summarized as first learn the partially observed solutions and then learn the functional form P of the PDE. So the first step is to interpolate and regress the input-output data on those partially observed solutions with some kernel K defined on the input space of U, which is equivalent to approximating those partially observed solutions with minimizers of the following optimal Relax variant. So this is essentially kernel ridge regression. And then once you have interpolated your partially observed solutions, you take the derivatives of the interpolants of those partially observed solutions to obtain approximate input-output data for P. And then you regress the approximate input-output data for P with your other kernel gamma, which is equivalent to approximating P with the minimizer of the following kernel ridge variational problem, right? Okay. Now, one thing that I want you to observe is that when you use this two-step method, nowhere you are using the fact that all these UMs must solve the same PDE, right? So you're discarding information, right? You just interpolate them without using the fact that they're solving the same PDE. But if that PDE is a polynomial PDE, that's a lot of constraint on these UMs. That's what you're discarding. Therefore, it makes sense to pursue another method, which is something that we call the one-step method. But before I go to the one-step method, let me just mention that this two-step method that I just described can be viewed as a kernel/GP analog of SIMD PDE find. And this kernel method is different in three directions. The prior knowledge about P is encoded into the choice of kernel gamma, whereas in SIMD this information is given by a dictionary. SIMD looks for a P that is sparse in a dictionary. The kernel method finds a minimum RKHS norm solution that is not necessarily sparse. The kernel method naturally accommodates variable coefficients PDEs, and for SIMD it's not trivial to deal with these variable coefficients, since variable coefficients may depend on Y in a complex manner that is not sparse in a particular dictionary. Okay, so what I said earlier motivates going to something that we call a one-step method. And here the idea is to learn those UMs, those partially observed solutions, and the functional form P of the PDE at the same time. And we do so by approximating those partially observed solutions and P with minimizers of the following nonlinear optimal recovery problem, in which the loss is the sum of the RKHS term squared of the unknown functions, and the constraints are enforcing the PDE at the points, the collocation points at which we are observing the source terms, and they're also enforcing our observation of the partially observed solutions at these observation points. We also consider the relaxed variant here. So this is equivalent to completing the following computational graph by simply replacing these unknown functions by Gaussian processes, independent Gaussian processes, and computing their map estimator. And again, this type of solving type 2 problems is generic. I'm just doing it for learning PDEs. Any problem that you can formulate as a graph completion problem, the solution is going to be the same, and you will have the same guarantees because of this compactness that I just described earlier. Okay, so connections with existing methods. What I'm describing here is, in some sense, a generalization of a paper with Tifan Chen, Bamdad Hosseini, and Andrew Stewart. You are also going to find other one-step variants. There is a one-step SIMD variant, which is known as weak SIMD or SIMD UQ. And the sparse pins method that I just described earlier, that's a one-step method, right? It's you recover everything at the same time. Now, what sets this one-step kernel method apart is that the kernel-based optimal recovery formulation leads to a stable algorithm that is amenable to second-order optimization. What it means in practice is that you don't have to wait forever to get your solution, because gradient descent takes forever. It accommodates a larger number of features and more flexibility in choosing and tuning the features for both the partially observed solutions and the functional form of the PDE. And it is readily defined with variable coefficients PDEs in mind, which is something difficult for dictionary-based methods. Okay, and I will give you illustrations of this point. Okay, so now let me give you some a theorem for error estimates. So for this theorem, we're going to assume that the domain of the PDE is bounded with Lipschitz boundary. We're going to assume that the RKHS space defined by the kernel K is continuously embedded in some subspace H gamma for some gamma greater than the dimension of the domain of the PD over 2 plus the order of the PD. Again, we need this to make sure that the PD is defined in a classical sense for the elements of the RKHS. Then we're going to assume that the RKHS space defined by the kernel gamma is continuously embedded in the subspace H eta for some eta greater than the dimension of the input space of P over 2. This ensures the fact that the elements of that RKHS space are continuous functions. And then we're going to assume that the elements of that RKHS space defined by the kernel gamma are locally Lipschitz in the following sense in a subset of the input space of P. Okay, then to state the theorem, I'm going to need two quantities. One is the mesh norm between the observation points of the partially observed solutions. So this is the field distance between these points, the resolution, if you want. And the other one is going to be the mesh norm between the partially observed input points of P, right? So this is, again, another field distance, but this is in a defined in a subset of the input space of P. Okay. And then we have the following theorem that essentially bounds the error that we make in approximating those partially observed solutions and the functional form of the PDE with powers of those mesh norms, right? So in the first inequality, you only have the power of the mesh norm between the observation points. This power corresponds to the gap between the assumed regularity of your partially observed solutions and the strength of the norm being used to measure accuracy. Here you have the same term, but you have another term. Here you have the power of the mesh norm between the partially observed input points of P. And again, the power here corresponds to the gap between the assumed regularity of P and the strength of the norm being used to recover P, which is here the sup norm. Okay? So again, those type of inequalities, if you're familiar with kernel methods, they're fairly classical, right? They are the same kind of inequalities that you see in scattering inequalities with kernel methods. They're essentially based on generalization of Poincaré inequalities. Okay, now let's look at the operator learning. So for operator learning, we want to approximate the solution map of the PDE. The dominant paradigm is to approximate the solution map via regression between spaces of functions using the FI UIs as input-output data. And two popular choices with neural networks will be FNO or DeepNet. But you can also see that kernel/GP methods can be competitive for solving this kind of tasks. So I don't know. So one thing that we were discussing earlier is that the funny thing is that actually kernel methods were the first to do operator learning. And I know, Florence, you mentioned a paper by Schwartz, 1960 or something, 1950. This is the one that you mentioned, right? Yeah. Schwartz, 1960. I didn't know about it, so I thought that we started doing operator learning with kernel methods in 2010, but apparently no, much earlier than this. But it's making a comeback. Well, the problem with this method is that they are incapable of handling scarce data problems. So with the level of scarcity that we are going to consider, you cannot do operator learning this way, right? You have to use some structure or information about your problem to actually recover the solution operator. Now, one naive idea will be to approximate the solution operator by inverting the learn PDE. This will not work. Why? Because the learn PDE may not be invertible, since the learn PDE is not guaranteed to be well posed. Okay? Well, the proposed approach is for a new source term f to approximate the corresponding solution by solving the learn PDE with a GP/kernel method, which has been introduced in this paper with Yifan Chen, Babel Hosseini, and Andrew Stewart, which can be summarized as completing the following computational graph that describes essentially the learn PDE, which is equivalent to approximating the solution corresponding to this new source term with the minimizer of the following nonlinear optimal recovery problem, in which you minimize the RKHS norm of the approximant subject to the learn PD being satisfied at a bunch of points, right? And that is regularizing your problem. So although the learn PD is not well posed, the regularized variant is well posed. It is not only well posed, it is guaranteed to converge, and you have the same kind of error estimates as the one that you have seen earlier on. So here the assumptions that you need is that you need the solution operator to be locally Lipschitz in a neighborhood of your new source term. And you need the new source term to have a solution that belongs to a subset of the input space of P where you partially observe input points of P become dense, right? If you have these two things, then you get those error estimates that look like very much like what you had seen before, right? But here you just have the RKHS norm of the corresponding approximant. That's it. Okay, so some numerical experiments. To describe these numerical experiments, I'm going to use three types of testing errors. One is known as a filtering error. So this is the error in recovering the partially observed solutions. Another one is going to be an equation learning error, which is the error in recovering P. And another one will be the operator learning error, which is the error in recovering the solution operator. Now, first example, we're going to consider the Duffing oscillator, which is the following ODE. We are going to take an RBF kernel, like a Gaussian kernel for U, for K. And for gamma, we're going to pick a polynomial kernel, which makes sense because this is a polynomial. And we are only going to observe one source solution pair, so we're going to do one-shot learning. This plot is showing the true solution versus time in red. The training data as blue dots. The interpolant is shown as a dashed line, so it's not accurate. And in black is what you get with this one-step method, right? And you get more accuracy because you are using the fact that this interpolant must solve an ODE that is polynomial. That's a lot of constraints, right? That's why you can recover things. Now, those are the extrapolated solutions using the learn ODE. In red, you have the truth. In black, you have the one-step method. In green, you have the two-step method, and in blue, the Cindy. And those things are not accurate because, again, that two-step method, you are trashing information. You're trashing the fact that these UIs must solve a PD that is a polynomial, which is why they are not accurate. Other example, the Burgers PDE. So here, we are going to choose an RBF kernel like a Gaussian kernel for K, for U. A polynomial kernel for gamma. Makes sense, the PD is a polynomial. And we are also going to do one-shot learning. So M is equal to 1. M is the number of source solution pairs. This plot is showing the training solution along with n random observation points in red and collocation points in white. So here you have 20 observation points, 50 to 100. You are in the scarce data regime here. Okay, so these plots are showing the filtering and equation learning errors, filtering, equation learning. And in blue is what you get with sparse pins. In red is what you get with Cindy. And in green is what you get with this one-step kernel method. And those thicknesses correspond to the average and best and worst errors with respect to randomization of the observation points, right? So you have some randomness because you are randomizing the observation points. Now, we are going to do one experiment. So for each of these methods, you have some hyperparameter tuning, right? You tune the hyperparameters of your kernel method, you tune the hyperparameters of your neural network, and you tune the hyperparameters of Cindy. Now, but you do it only once, right? And then you don't keep doing it as you randomize the points. But now I'm going to do an experiment. I'm going to randomize with respect to the observation points, and I'm also going to randomize with respect to the initial condition of the PDE that defines the data that we have seen. But I'm not going to retune the hyperparameters as I do that. I'm going to do it once. If you do that, then this is what becomes of your neural network method. The convergence plot becomes flat, completely flat. Right? So what this thing is telling you is that these neural network methods are not robust to hyperparameter tuning, which means that minimizing the loss of your neural network is not sufficient to get convergence. You need a human in the loop during training, right? So convergence of a neural network method is not minimize the loss, is minimize the loss plus put the right person to watch the training. And in fact, if you're familiar with these neural network methods, or with what OpenAI is doing, you know that they have, when they train the large models, they have 80 people watching the training live, right? And they decide when to stop. And they essentially rely on implicit regularization in doing so, whereas the kernel method is relying on an explicit regularization, which is why you don't necessarily need the human in the loop. Okay, other example, Darcy's slow PDE. So here this PDE has a variable coefficient A. Here we choose an RBF kernel for U, Gaussian kernel. And here we have to use a kernel that encodes the fact that this PDE is polynomial in U and its partial derivatives, but the coefficients are not constant. They are fields, they are functions. This is something hard to do with a dictionary, but with a kernel method, it's, as you know, it's very easy. You simply take your kernel gamma to be the product of two kernels, an RBF kernel in Y and a polynomial kernel in U and its partial derivatives. Here, the number of data points is going to be 2, 4, and 8. So again, we are in this. Yes?
So you seem to be tailoring the gamma curve to the problem.
Yes.
But if you didn't know the full problem, how could you tailor the gamma curve?
You have to be, you go bigger. So you typically use things such as additive kernels, meaning you have a best guess of what the true P would be, and you choose this as your first kernel. Then you add another kernel.
But if I misspecified the curve, would it have been disastrously bad?
In terms of accuracy, you will do worse.
Well, I know you'll do worse. But I suppose the question is, how much worse? And is there a way of finding what the right curve is?
Yes, yes, yes. How much worse? How much worse? As you get a lot of data points, all these methods are going to converge. In the high data regime, not much worse. In the low data regime, a lot worse, especially if you extrapolate. If you extrapolate and you use the RBF kernel is going to revert back to its mean, which is 0. And here you're going to do a lot worse when you extrapolate. The polynomial kernel will just continue its merry way in a polynomial way. And there you will do well. So again, high data regime, not a lot worse. Low data regime, a lot worse. How can you find out which kernel to pick? Again, the way you do it is that you typically use additive kernels, meaning that you say that, okay, maybe this P is a polynomial with variable coefficients, or maybe it's entirely fully nonlinear, right? It's something that is highly complex. So you can take your kernel gamma to be of this form, plus something else that will capture an arbitrary PD. Then you solve your problem, and because your kernel gamma is the sum of two kernels, the P that you will recover will be the sum of two P's. And then you can go back to these two P's and you can compute their individual RKHS term squared. And you divide by the RKHS term of the sum squared. And this will essentially define a quantification of how much each one of these individual P explain the variance that you have seen in the data. And if you are well specified, most of the variance in your data will be explained by this, by this quasi-polynomial kernel. If you are misspecified, the second term is going to explain what you have seen, right? Then you know that you're misspecified. That first term is not enough. And if you see that the first term is enough, what you do is that you kill the second term, you do it again, and you realize that your RKHS term remains bounded. Therefore, you are well specified. You're good to go. Yes.
So when I pick process, I usually pick up a mean function. So could you use a mean function if you knew something about the solution of the mean
Yes.
to actually improve the fitting of the counting process?
Yes, yes. You will actually improve accuracy in doing that. So in fact, the way we solve the optimal recovery, the infinite dimensional optimal recovery problem is a bit like this, in the sense that we use a Levenberg-Marquardt algorithm, which is iteratively changing the mean of our GP. So this is actually the correct way of getting a second order scheme for minimizing the underlying variational problem. Thank you. Okay, so those are the training tuples, observation points in red, collocation points in white. The number of observation points is 2 here per solution pair, 4, 8. So here you're in a very scarce data regime. Cindy and sparse spins will simply not work. You really need an optimal recovery method to make these methods work. These plots are showing the operator learning errors. The dashed lines correspond to the two-step method, and this dark line corresponds to what you get with the one-step method. This axis corresponds to the number of source solution pairs, and here you observe 2 points per source solution pairs, 4, 8. So you see that you converge, right? To converge, you need m to go to infinity and n to go to infinity. So you get your convergence. Okay, so this is what I was saying. At the end of the day, you have to minimize this nonlinear optimal recovery problem. So the way you do that is by invoking a representative theorem that looks like this, that allows you to represent those partially observed solutions or their approximate with expressions that look like this. So this is an expression involving your kernel K. This coefficient alpha becomes an optimization variable. This is for P, this is your kernel gamma, and this alpha appears here. So you see that you have a nonlinearity that is going to appear here. And this beta becomes also an optimization variable, right? This expression is going to involve pointwise evaluations of your kernel K and its partial derivatives. And the partial derivatives of K that appear are the ones that you assume to be present in your PDE. So you take these representative formulas, you plug them back into your optimization problem, and you get an optimization problem that looks like this. So this is nice, this is quadratic, except for this, but this is not that painful because you can iterate. This is still nice, it's quadratic and alpha. This one is not nice. This has a beta here and alpha here. This is non-quadratic, this is nonlinear. So what you do here is that you use an iterative scheme in which you essentially linearize this nonlinearity that you have seen here. So this is the nonlinearity that we have here. And what we're going to do is that we're going to linearize it at each step. But if you do that, that's not enough. Your method may be unstable. So here what we have to do is to use a variant of the Levenberg-Marquardt algorithm in which we introduce a quadratic penalization on how far we go from the previous step in beta and alpha. So this is kind of changing the mean of the PD, right, as you go through the iterations. And this leads to a stable algorithm, and it's essentially interpolating between a first order method and a second order method. So it's quite fast and it's stable. So it works well. Okay, so examples of applications. One which we are doing in collaboration with JPL and University of Washington concerns the identification of a PD for Jupiter's radiation environment. So here, the PD that we try to learn, we believe it to look like this, where those D and C are variable coefficients. But again, we are not sure. There may be extra terms. So we have to go through the discussion that we just had. So we actually had this very discussion with folks at JPL. They say, yeah, maybe it looks like this, but there may be extra terms. So we use these additive kernels to find out. And the problem is to learn the partially observed solution F and the structure of the PD and the coefficient fields. Another ongoing collaboration with USC and University of Washington is the identification of the law of stress transfer for earthquake dynamics. The problem is to learn the structure of the PD, which we believe to look something like this, the coefficient fields, and mostly the people here are interested in an ensemble average PD that describes the core scale dynamics after averaging over fault structures. So here the idea is that you may not have a PD at the there is a PD at fine scale, but what they are really interested in is some kind of homogenized PD for earthquake dynamics. They don't know if this homogenized PD exists, but you could try to learn it using the kind of techniques that I just discussed. Another example concerns subsurface fracture networks. So this is something done in collaboration with Adrian Prof, Jonas Achter, Alice Barker, Nathaniel Trask and Daniel Tataskowski. So it was mostly done at National Labs in Stanford. And the problem is, given boundary data, estimate the hydraulic head and flow velocity across the entire domain and provide 95% confidence band on estimates. So because you are using a GP method, you don't have only access to the map estimators of the solutions, you also can use the posterior distribution of UGPs as some measure of uncertainty, and folks at the National Labs were interested in this. And in fact, you can actually show that as you get more and more data, your posterior distribution starts to look Gaussian around those map estimators, so your Laplace approximant to the posterior distribution becomes valid. So it makes it easy to compute these posterior distributions if you use the Laplace approximant, which is equivalent to linearizing your problem around the map, essentially. Other example of application will be the identification of a modified Newton's law for explaining the discrepancy between observed gravitational effects and the amount of visible matter present in galaxies and galaxy clusters. The observational stars and gas at the edges of the galaxies rotate faster than predicted by the gravitational pull of visible matter alone. Without additional unseen mass, these galaxies will fly apart. So a fix for this is to assume that you have some matter that you don't see. It's called dark matter. And another fix is to change F equals ma, Newton's law, and assume that Newton's law is actually not valid at very small acceleration. The problem is that you have very small data, so you have very small and a very low data regime to learn this modified Newton's law. Another example of application, so we are not working on this, but I think this could be interesting. It would be to learn a PD for magnetic confinement fusion reactors, so tokamaks, for instance. Now, if you have worked with this tokamaks, you know that we don't have good predictive theories for them because they operate in extreme environments. And the idea will be to learn a good predictive theory from that. That will be interesting. Okay, now I'm ready to move to type 5. I don't know how much time I have left. Jack, shall I do? I will just give you some high-level ideas. So, okay. So the example of type 5 problem that we are going to consider here is that of discovering an algorithm to solve a specific problem. And what I'm going to present is a joint work with Theo Bourdet from CALTECH, Abenaya Gadana Sekaran, and Twin Sai from SRI. And this stemmed out of a DARPA project led by Yannis Kavrakidis, whose focus was on the mathematics for discovering algorithms and architectures. So the idea is to discover a method for discovering algorithms. In the beginning of this project, I thought, yeah, I will always be able to beat whatever a machine can do in terms of discovering algorithms, because discovering algorithms is really the most creative thing that we can do as scientists. And this was the case in the beginning of the project. At the end of the project, I don't think that this is the case. I think that these things are going to beat us at developing algorithms. So this made me kind of excited, but also worried because of what you can actually do with these algorithms. Okay, so now let me unpack this a little bit. So the current paradigm for automating algorithm discovery is direct code generation with an ensemble of large language models, this combined with a pool of possibly human or non-human evaluators and evolution or genetic algorithms. Okay, what do I mean? If you are using ChatGPT, you know that this thing is really good at coding, right? You can ask it to code a solution of the Laplace PD for you. It will just generate a code for you. So the idea is that instead of having one ChatGPT, you have 1,000 of them. You give it a problem to produce an algorithm for. So you have 1,000 large language models that will produce an algorithm, a code, actually a Python code to solve your problem. Then you have human or non-human evaluators that will evaluate this thing. And then you keep some of them and you kill some of them. And the one that you keep, you tweak, right? So it's your classical genetic algorithm applied to large language models. This is the current paradigm. The latest variant of this paradigm is known as AlphaEvolve, and it's basically a scale variant of something that was proposed earlier on in these papers, right? So this is what you're currently doing with your ChatGPT if you're using that. Now, what we are proposing is essentially something that we call a computational language processing framework that treats computation as a learnable language and operates at the computing level than at the code generation level. So essentially what we are going to do is to create a language that speaks algorithms. You give it a problem instance, and it will speak an algorithm for you to solve that problem. But it has to learn the language by itself. There is no prior data, and I will show you how it learns the language by itself, right? Now, claim this approach is more efficient because learning occurs at the computation level rather than the code generation level. And as a consequence, it can generate an algorithm not only for the problem class, but also for each instance of the problem. So it circumvents the no free lunch theorem that states that no single algorithm can universally outperform other across every possible problem instance. So what do I mean? If I give you PD to solve, you use an algorithm for the problem class, like the finite element method. You never really look at the particular problem, the coefficients that you see, or I'm going to actually adapt, really fine-tune my algorithm to the underlying problem that I'm going to solve. So this is what this method is going to do. It's going to look at your particular instance of the problem and speak an algorithm for that particular problem instance. Now, this framework is going to conceptualize an algorithm as a string of elementary computational operations, which we are going to call primitives or tokens, so this in analogy with language models. And these tokens are going to be chained with a precise computational grammar or syntax. So an algorithm is essentially going to be a chain of these tokens, and these tokens are going to represent computational operations, right? And you know that to chain computational operations, they have to fit, right? The output of one has to fit with the input of the other one. Okay, now this framework does not require prior data. It's going to teach itself how to speak or generate algorithms. To do that, starting with elementary primitives or tokens, it's going to discover new tokens and algorithms by using Monte Carlo tree search plus reinforcement learning as a babbling mechanism to search over the tree of all possible strings of tokens, right? So in that tree, the edges represent these tokens or the computational actions, and the nodes represent the state of the computation. Okay? Are you all familiar with MCTS, Monte Carlo tree search? Do I need to give you a reminder? Don't be shy. I can raise your hand. Yeah? Okay. So what is Monte Carlo tree search? Assume that you want to find the best restaurant in Cambridge. What is it that you do? You have a choice of possible restaurants. Each time you go to the restaurant, the cook may be in good mood or bad mood, so you don't exactly get the same thing, right? You get a sample from a random variable. So essentially, you have a choice of possible actions. Which restaurant do I go to? Each time you go to a restaurant, a sample from a random variable. And ideally, I want to find the restaurant whose random variable has the highest mean, but I don't know the mean of that random variable. It's unknown, right? So I have to keep coming back to that restaurant to sample again to compute an empirical mean, and hopefully that if that empirical mean is the highest, that's the one that should be going to, right? So what is the best strategy to use to find the best restaurant? So this is known as the bandit problem. And the way you solve it is that you go through a trade-off between something that you call exploitation or exploration. Exploitation meaning that you have already visited 5 restaurants. Among those 5, there are some that you like, right? So there's this one that has an empirical mean that is here. The other one has an empirical mean that is here, but you're not really sure that this is still the best because maybe the cook was in a bad mood, right? So if you keep going, maybe you see the empirical mean shifting. And then you have the other ones that you have never been to, right? So essentially, this bandit problem has a formula where you choose a restaurant based on the best one that you have seen so far, so this one, and based on the ones where you have a lot of uncertainty. So if this one I've never been to, I should visit it and get some kind of feel for how the cook is. And if I've visited all of them, then I'm relying on empirical means, but these empirical means are stochastic, right? So I believe this one to be the best so far, so I should be going to see this one, but maybe I have only a few samples for this and also a few samples for this. So the uncertainty between them could be high, right? So then I have to maybe visit that one. So this is the bandit problem. It has a no regret approach to solving it. So minimum regret in a limit where you go to your restaurant infinity often. You can show that you minimize your regret. And Monte Carlo tree search is essentially a hierarchical variant of this, right? meaning that you have a choice of restaurants at the first level, then second level, the third level. And the way you do it is that you, instead of you go through this down this tree, and as you go down, you essentially sample some underlying variable, and then you get some kind of estimate of the value of the node at the bottom of the tree. Does it make sense? Okay, so this is Monte Carlo tree search. What we are using here is an ensemble generalization of something known as the AlphaZero engine. So AlphaZero is the engine that was proposed by DeepMind for playing board games, right? You have heard of it when they were playing Go. Basically, what they did is that they took this MCTS algorithm and they combined it with two neural networks. One that you can call the policy network, and the other one that you can call the evaluation network. So what the evaluation network does is that it looks at this chain of possible moves, and at some point you cannot never, if you play Go, you can never go down all the way down the tree because the number of moves is just too large. So at some point you need to look at the configuration of your board game and decide and give it a score, right? So this is what the evaluation network is going to do for you. It's going to score the board game for you. And there is another network that is essentially going to look at the current state of the board game and make some proposed moves, right? And it's doing so based on this bandit problem that I was describing earlier on. So at a high level, this is what we are using. We're using the same engine, but we are coming up with an ensemble variant. Why? Because here for us, the nodes may contain an ensemble of computational states because these computational actions may be stochastic. So for instance, if you're solving an optimization problem, you may be using a simulated annealing and the result is stochastic, or you may be randomizing your optimization problem at random, again, initializing your optimization problem at random. So some of these actions are going to be stochastic. Now, so for the RL part, the policy network is going to output a distribution on the next computational token, and the value network is going to estimate the value of the current computational state. Okay. So now, another element that we're going to use to learn this language is something known as byte pair encoding to create new tokens from low-level tokens. So what do I mean? So starting with a set of low-level tokens or computational actions, we're going to solve an ensemble of instances of the problem, and I will give you examples of that problem, by combining low-level tokens with MCTS plus reinforcement learning. Out of this, we're going to get an ensemble of strings of low-level tokens, or if you want, an ensemble of algorithms. And the token pair that occurs most often in this ensemble of strings is going to be replaced by a new token. So for instance, if you see that the action AB occurs most often, then we're going to call this a new token E, and then this E will be added to the alphabet of vocabulary for the next iteration. Okay, simple. So these two things, MCTS plus RL plus byte pair encoding, which is something that typically you use in language models. But again, here we don't have data. We teach ourselves to speak algorithms. Okay, so what this framework is automating and amplifying is the same strategy that was employed for the discovery of turbocodes. Turbocodes have transformed digital communications by enabling efficient and reliable data transmission close to the theoretical maximum. And according to their inventors, so Claude Bérou and Alain Glavieux, turbocodes emerge as the result of an empirical, painstaking construction of a global coding-decoding scheme using existing bricks that had never been put together in this way before. So basically what they did is that they took bits and pieces of algorithms and they tried to put them in the right way, right? But it's a very slow process if you try to do it by hand. But you can amplify this process a lot and you can accelerate it a lot if you use a machine. So this is essentially what we are doing. And this is the part that made me worried, is that at the end I realized that, yeah, we cannot compete eventually with a machine doing this for us. Now, let me give you some examples of applications. So in the first example, we are going to generate algorithms for solving the quadratic assignment problem. which is the problem of minimizing the following loss over the set of all permutations of 1 to n. So this loss is defined by these three n by n matrices, D, F, and C. And again, we're trying to minimize this over a set of permutations of 1 to n. This is a strongly NP-hard problem, meaning that getting within a constant of the optimum is also NP-hard. So in fact, if you have played with this problem, you will see that for n equals 20, it's already super hard, right? It contains the traveling salesman problem as a particular easier cases, and it also contains the graph matching problem as a particular case. Many other combinatorial optimization problems may be written in this form. Okay. So applications of the quadratic assignment problem include supply chain resource allocation and optimization in logistics. I gave a DoD talk, so that's why I have this slide. I will not linger on it. And other examples include facility layout location, data center optimization, very large scale circuit design, and radar packing problems. So those are examples of applications. Now we are going to apply this framework. So starting with a small number of low-level primitives, such as gradient applied to the loss relaxed to doubly stochastic matrices, linear sum assignment, negation identity, convex combination, for loop, 2 CT flips. So those are very basic operations that you can do on your permutation matrix or its relaxation to doubly stochastic matrices. And those are going to define our primitives. So starting with this very small number of low-level primitives, this framework with byte pair encoding is going to discover increasingly more complex and effective algorithms identified as dominant strategies or dominant strings of tokens. So this is what this plot is showing you. I'm going to unpack it a little bit. So in the x-axis, what you have here is the number of iterations, and you have a round of byte pair encoding where you create a new letter for your alphabet every 10 iterations. And this is marked by a vertical line. The vertical axis are showing the frequency of each token and the average optimality ratio. So this, you want it to be small. And essentially what you see is that as you play the game, you have specific strings that become dominant, right? And one of them that will become dominant is this one, where you take a doubly stochastic matrix and you take the gradient of the loss at that doubly stochastic matrix and you apply linear sum assignment to it, and you take a linear convex combination with the previous value of that doubly stochastic matrix. This thing is rediscovered automatically with this byte pair encoding. And in fact, this thing is the default SciPy solver for the quadratic assignment problem. It's known as the Frank-Wolf algorithm. So you essentially learn it from scratch. But you are not limited to just learning that. You are going to learn new algorithms as well. So how well does it work? To describe this, we apply the problem to two instance generators. One is known as the composite QAP, which is an average hardness instant generator. Another one is known as the Palu-Bekis QAP, which is a hard QAP instant generator. And we're going to compare the proposed framework, which we call CLP, with simulated annealing, branch and bound, and GuruB. So GuruB is the SOTA commercial platform for mixed integer programming and optimization. So this is how you would do for this average hardness instance generator. Essentially, up to problem size 80, the proposed approach is going to solve the problem exactly. And it does so in real time. This is what you get with simulated annealing, and this is what you get with GuruB. This is for the hard instance generator. Here you're going to solve 99% of all the problems, and GuruB is what you get here. Okay. There is also a library of benchmarks for the quadratic assignment problem if you're into that thing. It's called QAP-lib. And here, CLP will solve 41% of those problems. And it will beat or equal all other tested methods in 94% of these instances. again, this is why so in the beginning of this project, I could imagine an algorithm that will beat anything that a machine could do. I don't think that we can do it now. It is hopeless. Now, another example of application is to generate an algorithm for the quantum search problem. The quantum search problem is to identify a target element in an unstructured set of n elements with a minimum number of queries to an oracle function operator. So the idea is that you have a set of n elements, doesn't have any structure, and you have an oracle function that returns 1 if the x is the right one, the market state. In fact, what you have with this oracle function is an oracle quantum operator that acts like this on a quantum state. And the problem is to quantify the mark element with a minimum number of queries to the oracle function. So the classical solution is an exhaustive line search of n, and the quantum solution goes back to Grover's, 30 years old. It's Grover's algorithm. It requires pi over 4 square root of n oracle queries. So we apply the framework to this. And here the primitives are naturally the quantum what you call quantum gates, which are, so you have a natural set of quantum operations that you can perform on your quantum state, and this becomes our computational actions, essentially, that we're going to try to assemble. And using quantum gates as primitives, this framework discovers an algorithm that rigorously reduces the number of layers by a factor of 2. Now, this is significant because the number of layers has exponential impact on errors. Okay, so when we did this, not our DARPA program manager, but for DARPA program manager for a different program that was focused on quantum computing, said, yeah, but you have kind of solved a spherical horse, meaning that quantum search problem is an easy problem. There's a harder one, and they told us, try to generate an algorithm for the quantum approximation optimization algorithm, which is a hybrid quantum classical algorithm, right? So the idea is that you have a objective that is classical, and you encode it into a quantum Hamiltonian, and you try to minimize the quantum Hamiltonian. I will not go into the details. I don't want to bore you to death with this. The only point that I will try to make is that you can actually implement this framework here, and if you do, you get a 35% average improvement over adapt QoA, which is the popular variant of QoA implemented within NVIDIA's quantum computing library. So it kind of works. Okay, let me skip this. And if I have 1 minute, I will finish. So other applications on examples of type 5 problems include mission planning, system engineering, engineering design, drug discovery, math discovery, architecture design, analog computing, drone coordination and control. Some of these examples are not naturally amenable to sequential graph generation or reasoning. So here I want to tell you where this complexity ladder is taking us. An example of such problem is mission design. So this is something that we have been looking at with NASA and JPL. And the problem here is to design a digital twin for a NASA space exploration mission whose objective is to detect signs of life on Enceladus, which is the moon of Saturn. And this is a CALTECH Kickstarter collaboration. Now, this solution cannot be sequential because it requires the generation of multiple interacting graphs at various levels of complexity. And these graphs correspond to things such as science traceability, instruments, spacecraft, Enceladus geophysical systems, human processes, encoding cost, power systems, control, etc. And the whole expertise is decentralized. So if you actually watch NASA engineers trying to solve a problem like this, you will see that they are not doing it in a sequential manner, right? They're trying to generate these graphs, and they go through multiple iterations where they have these multiple graphs that are trying to generate, that they must, and all these graphs must interact with each other at the same time. Now, this framework that I just described has been based on a sequential tokenization of algorithms, as large language models are based on sequential next token predictions. And to solve these more complex type 5 problems, we need a generalization of CLP to non-sequential modular hierarchical generalization of computational graphs. Where is this thing taking us? Well, humans have two forms of reasoning: left brain, which is sequential, detail-oriented, analytical, and right brain, which is holistic and intuitive and achieving non-sequential graph generation. I think would lead us to a more holistic and intuitive right brain form of AI. That's it. Thanks for your attention. Thank you. Yes.
Works by
Yes.
It has also fractional order pins.
Yes. Yes. Yes.
I'm thinking if your approach is capable of this one.
Yes.
Taking into account the order of the
Yeah.
also subject.
Yes. Yes. So first, fractional derivatives are still linear operators. So the setting applies. And what you're asking is, what if the order of the fractional derivative is an unknown parameter? It will apply the same. So what you do is that you make that unknown parameter an unknown variable. You replace it by a Gaussian random variable that you infer using map estimation. So you will end up minimizing the norm squared of that unknown parameter. It will work.
In this respect also, you mentioned that Newton's law that is not accurate, doesn't hold all acceleration.
That's a conjecture. That's
Never hold, because we have in friction and only present energy dissipate. So basically, Newton's laws are just a model that has a limited range of applicability. And instead of, for example, that acceleration that is second order derivative, you should consider derivative of order between 1 and 2 to take into account those.
Mm-hmm.
And the same is with the case of Newton's fluids and everything.
Mm-hmm.
So there is that range of applicability. So for me, it is not any surprise that something
Yeah.
was
Yeah. So we have our collaborators at USC that are telling us exactly the same thing, that you should actually look at this fractional order PDEs that explain nonlinear transport in porous media, because these things, in fact, once you take an ensemble average, you get these scaling laws that correspond to these fractional order PDEs. Yeah.
Also, I was thinking about those Monte Carlo things.
Yes.
Is in his recent works, when his group is using the method that we developed with Nikolai Leonenko here a couple of years ago, Monte Carlo method for fractional order differentiation. So he is now using this for his fractional pins.
Yes. Yes. Yes.
I
Yes.
was thinking about those Monte Carlo tree search, like if there is any link on. This is just
Yeah, so I'm not familiar enough with what would they do with Monte Carlo to answer this. So the way we use MCTS here is just to, find the right ordering of these computational actions. Thank you. Yeah.
I think in most of what you said, making sure all these AI are safe, trustworthy, reliable.
I think, yeah.
Ready to retire, but also we are teaching the next generation
Yeah.
of scientists to.
I think is all of this and all of the above is true. I mean, if you look at the emergence of scientific computing, in the scientific computing emerged in part out of Los Alamos, and they had teams of humans actually solving PDEs by hand. Now we don't solve PDEs by hand anymore. We let the machine solve the PDE for us, but we still understand what the machine is doing, right? I don't think that you want to let go of this, because if you actually let go of this, you may start losing your cognitive abilities if you rely on a machine to do the thinking for you. So far, I mean, if you use these large language models to code, you will see they are not very reliable eventually once your code becomes too large. So you still have to understand what you are doing. What is changing is that the level at which you reason about abstraction is increasing. And it could be a good thing if you keep track of the lower levels. I mean, at the end of the day, you see, 100 years ago, if I were to ask you to solve square root of 2, this is something that you will do by hand, right? Now, you never think of solving square root of 2 by hand. You use your pocket calculator. But you understand, I mean, you still trust it because you know what this thing is doing. Or let me give you another example. If you try to compute the mortgage payment on your house, 50 years ago, you will do it by hand. Now you use an Excel sheet. So it allows you, it essentially what it does is that it makes abstractions of the technicalities, and it allows you to reason at a higher level of complexity. And there is a quote that I like that says that civilization advances by automating the operations that can essentially be, I'm paraphrasing, that can be automated, right? So this is, we go through this process where we essentially automate all these things that are technicalities. The problem is that if you lose grasp of what is being done at a lower level, then you lose some of your cognitive abilities. And I think you can see it with some of these children. They cannot add numbers, right, or multiply numbers. I mean, I know I'm about 50, and at my age, we used to multiply numbers by hand. I don't know if people still do it, but so there was a book actually written by the CEO of Google, Kissinger, that was saying that one consequence of AI will be that a fraction of the population will start losing their cognitive abilities because they will let AI do the thinking for them. I think that will be a very poor outcome. How do you sell it to your students? The way I do it is that I try to teach them linear regression. So I can tell you at CALTECH what I teach is kernel methods, Gaussian processes, and I tell them, if you understand linear regression, you will understand most of deep learning. And they see it. I mean, once they see it, they realize it. And then they go to finance and they apply their methods where they compare linear regression with GNNs, and they realize that in the low data regime, linear regression will beat everything. And they say, okay. Oftentimes, that's all you need. Yes?
So it seems to be one of the advantages of simple is
Yeah.
that you end up with a set of PDE as a set of primitives that we understand the Gaussian process method, though it solves it really beautifully, and it's sort of interpretable. It isn't as interpretable as those primitive functions, which we can use to expand our understanding of what that PDE is actually about, what the physics works in it. Is there some sort of hybrid method we could build which did some type SIMD type thing to give you an approximation, and then you use the Gaussian process on a bit that hasn't been understood, and that adds that extra bit? So
Yeah.
approximately, it is this polynomial plus this. Is that possible?
Yeah, so if you use a polynomial kernel, then you get the interpretability of the P that you recover, because you recover a polynomial P. So this you have also for the kernel method. The difference is that SIMD use sparse regression, kernel method you use optimal recovery. You minimize the RKHS norm, but you still have that. But the kernel method allows you to augment this choice for P, right? You can start with the polynomial, and to that polynomial you can add something else. You could say, okay, I believe that this P is mostly a polynomial, but there is an extra term, I don't know what it is. I believe it to be a polynomial with variable coefficients, and I'm going to capture it with a kernel that looks like this. Or maybe it will be entirely nonlinear, and I will capture it with this second kernel. So this you can do with the kernel method. You can not only do that, and then you can go back and you can say, okay, the 90% of the variance in the data, I can explain it with my polynomial, but 10% is explained by this arbitrary kernel that I've added. So you can do that.
So the function processes you choose, so their RKHS will be very important whether you can recover this function or not. So the function, if the true function is not in the RKHS or like not in the closure, you won't be able to recover it, right? So like and then also there is also danger in like making the RKHS too big, because I think the learning rate would be slower. So how to handle this? And then you kind of need to be able to know what kind of function is actually involved to be successful. And secondly, about the uncertainty quantification that you mentioned, like I believe I believe you were working with noiseless data, right?
No, noisy.
Noisy data. So there's some noise in the observations. Okay, then it's fine. But otherwise, like then you cannot really have a posterior distribution if you don't have noise.
Yeah, so we work with noise. So concerning your first question, let me repeat it. The question is, if your solution is irregular, right, then it will not belong to the RKHS of your regular kernel, like Matern. Can this method be generalized to the setting where the solution does not belong to the RKHS? The answer is yes. So we have done it recently in a paper with I think I may have cited this paper early on. So in this paper, we have actually, so this is just for solving. You can generalize these kernel methods for solving PDEs, but with stochastic forcing. So you take the Laplace equation and you let the right-hand side be white noise, or even something less regular than white noise. So the solution is no longer smooth, right? It lives in H1 and even in L2. And you try to capture it with a Gaussian kernel or Matern kernel. And the question is, can you actually make the method work? The answer is yes. The way you do it is that first you don't use point-wise evaluations of the PDE, you use average evaluations of the PDE, and you don't enforce the PDE exactly. You do the relaxed variant. But in the relaxed variant, you don't use an L2 norm of the relaxation, you use a negative Sobolev space norm, meaning that the PDE is enforced at the collocation points or the collocation pair patches with respect to a very weak norm, which is typically like H minus S. If you do that, then you can actually show that the solution that you will get with your smooth kernel, like Matern, will converge in a weak sense. So you can make these methods work even though you have a smooth kernel with stochastic forcing or rough forcings. If you impose your PDE exactly and if you don't relax it, you will get an indication that you are misspecified by looking at the RKHS norm of your approximant and observing that this thing is blowing up, right? So you have two approaches. Your second question, so noise, yeah, so you can naturally include noise. Yeah, kind of, almost, but not quite. So if you look at the sausage, I don't know if you can see it's in pink. The sausage doesn't shrink all the way to 0 because there is still some residual noise. So to unpack this, you have this you have these pointwise estimates for interpolation errors, right? With GP methods. This is what we use, where you say that the pointwise error that you make with your interpolant is bounded by the RHS norm of the target function times the conditional standard deviation. What we do here is that we replace the RHS norm of the target function by the RHS norm of the interpolant, and the conditional standard deviation, we have it. And then you can do this in the setting where your data is noisy. That's essentially what you are seeing here. Thank you.